Happy learning! Today we're going to talk about graph colorings. All right, so what is a graph coloring? Let's start with the definition. A proper K coloring all right, so K here is representing just a whole number. So this could be like a proper 3 coloring or a proper 5 coloring. Okay, a proper K coloring of a graph G is an assignment of colors, okay, typically numbers, so blue wouldn't be one of the colors. 1 would be one of the colors. Okay, so is an assignment of colors to the vertices of the graph so that no adjacent vertices share the same color. Again, or number. And the last condition is that K colors, or numbers, are used. Okay, so this could be used to model, let's say you are, what was our last video? Stable marriages. Let's say you are hosting a wedding, okay, and you want to determine who's going to be at the same table, who's going to be at which table. Okay, so the vertices would be the guests at your wedding, and the color that you assign them would be their table number. Okay, so everybody who gets number 1 would be at table 1, and everybody with number 2 would be at table 2, and so forth. And maybe an edge means that these people really cannot be at the same table. They're not compatible with each other. Okay, so in that situation, a graph coloring could be used to assign tables. All right, so let's take a look at an example. Let's say G is the following graph. We can color this graph with 2 or more colors. Okay, so if we do the following, so 1, 2, 3, 1, 3, that's an example of a proper 3 coloring. Okay, if we replaced these 3s with 1s, that's still a proper coloring. It's just no longer a proper 3 coloring. It'd be a proper 2 coloring. No matter how hard we try, we can't do a proper 1 coloring of this graph, right? Because that would mean 2 vertices would have to, two neighboring vertices would have the same color, which we're not allowed to do. Okay, let's look at another example. Let's see if we could find a 3 coloring. Okay, typically we drop the word proper. So if we just say find a 3 coloring, that's implied that no 2 adjacent vertices will have the same color. All right, and so here's our graph. Oops. And let's see if we can color this with exactly 3 colors. All right, so here let's just start. I'm going to start by assigning this vertex to color 1. And now what do we know? This vertex is neighbors with 1, so it can't be 1. So I'm going to call it 2. And this vertex in the middle is neighbors with both 1 and 2. So I'm going to color it 3. All right, and I claim we could do this with 3 colors. So let's see if this continues. This vertex here could be 1. This vertex is neighbors with 1 and 3, so it should be 2, 1, and 2. And you could check that there are no adjacent vertices that have the same color. So this is a 3 coloring. And we could find a 4 coloring or a 5 coloring. That's a lot easier. And so a question that's typically asked, and we'll look at this in the next video, is what is the fewest number of colors needed to color a graph? That is, that's the graph's chromatic number. Okay? And so this graph actually has a chromatic number of 3. No matter how hard you try, you can't color it with exactly 2 colors. You need at least 3. All right, so we're going to look at, just very quickly, a special type of graph. And then we're going to state a very famous, but not very important, theorem in mathematics. Okay? So a graph is called planar if it can be drawn so that no edges cross. All right, both of these are planar graphs. But an example of a non-planar graph would be something like this. All right, it is a little bit challenging to prove that you can't just like rearrange the vertices and maybe get lucky and have none of the edges cross. But yeah, in this case, it is impossible to draw this graph without the edges crossing. And there's a ton of graphs that are not planar. But planar means you could draw them with the edges not crossing. All right, and so you can, now we're leaving the world of graph theory for a moment, and think if you were to open up an atlas, okay, or look at a map. Let's say you're looking at a map of the United States. Okay, we can take a region in the map, all these states, and assign to it a planar graph. All right, so I'm going to give you a very basic example. So suppose this is our country. Okay, so suppose this is a country and it has a bunch of states. We can, so this is not a graph. This is a map. Okay, so this is, but we can assign a graph to this map. Okay, so imagine we wanted to, you're a little kid and you wanted to shade this in so that no 2 neighboring states had the same color. The way we're going to do that is assign to a graph and give a proper coloring of the graph. All right, so how do we do that? Basically, each region would correspond to a vertex. So we're going to have 1, 2, 3, 4, 5, 6, 7 vertices. And then we'll have an edge between vertices if the regions are touching each other or are neighbors. Okay, so here we're going to have an edge. We'll have an edge. We'll have an edge. Okay, so this graph that I just drew, which I'll redraw below, is a graph that captures the same information as our map. I'm missing some edges. Sorry. These two regions are adjacent, so we'll have an edge like this and like that. Okay. But you could see we have a map and it becomes a planar graph. None of the edges cross. And so there's a very famous theorem in mathematics about planar graphs. It's called the four-color theorem. And the reason why it's so famous is not because it's like important and it has a bunch of applications, but it's the first theorem where humans or mathematicians took advantage of computers to aid in the proof. As in, they basically boiled it down to a bunch of cases and they had a computer check all of these cases and verify that the theorem was true. Okay, and historically, people weren't thrilled. They thought this is a disgrace to mathematics, but it's come to be accepted as a very, useful proof technique. And, mathematicians nowadays use computers all the time, of course. Okay, so what does the theorem say? It says, this is called the four-color theorem. It says any planar graph can be colored with four or fewer colors. So no matter how complicated you make a map, you can color in the states or the countries so that no neighboring states or countries have the same color. And you only need four or fewer colors. Okay? So we could do that. We could do that here just really quickly. Here is our region. Let's see if we could color this. So the theorem claims we could do it in four or fewer colors. That doesn't mean it's easy to, but it's possible. All right, so maybe this vertex will color 1. I feel like my graph wasn't quite right. This vertex does not neighbor that one, so we're missing that. Okay, this we could label, so 1, 2, 3, 2, 3. We could label this one 1. I think we're going to be able to do this one in 3 colors. This could be 2. Oh, okay. My graph is totally wrong. Sorry about that. Okay, there's 7 regions. I only had 6 vertices. Okay, this could be labeled 1, and this could be labeled 3, for instance. So we colored this region in 3 colors. No matter how complicated we make the graph, we could do it in 4 colors. Sorry for the confusion there. As I was saying, it's not really something that mathematicians care about too much. But it's an interesting theorem because of the historical reasons with the computers and all. Okay, well, epic blunder, but happens to the best of us. Let me know in the comments if you have any questions, and I will see you in the next one. Take care. Bye-bye.